Today, we're going to introduce hypothesis testing. Hypothesis testing is a procedure that we use to analyze an assumption made about a population parameter. So here is a news article from Gallup. Gallup is a company that provides analytics and consulting to organizations. It's known for its public opinion polls. And if you're interested and you want to see this article, you can click on the PowerPoint presentation down here where it says Gallup. This is a hyperlink that will take you to the article. And so this article says, daily loneliness afflicts 1 in 5 in the US. So 1 in 5 is 0.2 or 20%. So the population of interest here is people in the US. Gallup says that daily loneliness afflicts 20% of Americans. Now, let's say that a researcher doesn't believe that 20% is the true percentage. How can the researcher disprove this statement? We're interested in coming up with a procedure to determine if this type of statement is true or false. High levels of LDL cholesterol can build up in the artery walls. And when you have high levels of LDL cholesterol, this increases the risk of heart disease and stroke. There's this medicine called Lipitor, which lowers LDL cholesterol levels in the blood. Now, how it works is it blocks an enzyme which is involved in the production of cholesterol in the liver. You produce cholesterol, your body naturally produces cholesterol. And so Lipitor will reduce those levels in your liver. Now, Lipitor can decrease LDL cholesterol concentrations by up to 61%. And I found this information just by looking it up on Google. I found an article from the National Institutes of Health that says clinical studies with this agent, Lipitor, have shown that LDL cholesterol concentrations may be decreased by up to 61%. Now, let's say you work at a pharmaceutical company and you've developed a competitor to Lipitor, and you believe that your newly developed drug is more effective than Lipitor at lowering high levels of LDL cholesterol. How do you prove it? What kind of test can you construct to help you show that your medicine for high levels of LDL cholesterol is more effective than Lipitor? So we're going to learn about hypothesis testing, which is a procedure or a framework that's going to help us prove these types of statements. In hypothesis testing, we have two hypotheses. The first hypothesis is called the null hypothesis, and we denote it as H with a little 0 in the subscript. And we call this the null hypothesis, or H0. And the null hypothesis is the position that is initially assumed to be true or is based on prior belief. It is a statement that is assumed to be true unless there's convincing evidence to the contrary. The alternative hypothesis, which we denote as H with a little a in the subscript, you can just say HA. The alternative hypothesis is the new perspective. It is a statement that is accepted as true only if there is convincing evidence in favor of it. Now let's go back to the article about daily loneliness. So we said daily loneliness afflicts 20% of American adults. This is from the news organization Gallup. Suppose a behavioral health company believes this percentage is incorrect, and they randomly sample 852 American residents and ask them whether or not they feel lonely on a daily basis. What is the null hypothesis? So the null hypothesis is what's told to us in the article, that the true percentage of Americans, notice that it's the true percentage because they're talking about all of US, that's the population. They don't say something like, out of 500 US residents, 20% experience daily loneliness. Instead, they say daily loneliness afflicts 20% of Americans. So this 20% is the parameter. And so the null hypothesis is P. Remember, P hat is a sample statistic, but just the letter P is the parameter. P is equal to 0.2, or you could write P is equal to 20%. What is the alternative hypothesis? This is the new perspective. This behavioral health company believes that this percentage is incorrect. What mathematical symbol means incorrect? Well, that's not equal to. So the null hypothesis is P is not equal to 0.2. We've seen this article before. CNN says that 33% of children worldwide are now nearsighted. Now, let's say a pediatrician believes the true percentage is lower. He conducts an eye exam of 160 children to determine the percentage that are nearsighted. What is the null hypothesis? The null hypothesis is what's given to us. It is the assumption. It is that 33% of the children are nearsighted. So P is equal to 0.33. Now, what is the alternative hypothesis? So we are told that a pediatrician believes the true percentage is lower. Lower means less than. So the alternative hypothesis is P is less than 0.33. Whenever you write a null hypothesis or an alternative hypothesis, you want to write it using these symbols. You don't want to write a sentence. You want to write P is less than, greater than, equals, something like that. Let's look at that example about Lipitor and the competitor. Remember that Lipitor reduces LDL cholesterol levels by up to 61%, and we have a pharmaceutical company who's developed a competitor, and they believe their drug is more effective. What does more effective mean? Well, if Lipitor can decrease by up to 61%, we would expect that this new drug would decrease concentration levels by more than 61%. So the null hypothesis would be either P is equal to 0.61 or P is less than or equal to 0.61. That doesn't really matter if you want to say equals to 0.61 or less than. This is the concentration levels that the new medicine can reduce. And the alternative hypothesis is P is greater than 0.61. And what is P in this example? It is the new medicine, and it's the concentration levels of LDL cholesterol. Now, how does hypothesis testing work? We know that we have a null hypothesis and we have an alternative hypothesis. Our goal is to try to figure out whether the null hypothesis or the alternative hypothesis is true. Now, since hypotheses are statements about a population, and usually a population is very large, we cannot actually determine the population parameters. So it's usually impossible to figure out which hypothesis is 100% true and which one is 100% false. So we're going to develop a testing procedure. And the way that we test hypotheses is similar to how a court decides whether a person is guilty of a crime. So we're going to think about the null hypothesis is the assumption that the person is innocent, and the alternative hypothesis, which is the new perspective, is the person is guilty. In a court system, we say that a person is innocent until proven guilty. And so we're going to think of the null hypothesis, whatever the statement is, that assumption, that is the assumption, it is true unless you can show otherwise. So the court and jurors assume a defendant is innocent unless the evidence provided shows the defendant is guilty. If the evidence does not support guilt, then the jurors fail to reject the null hypothesis. What does fail to reject the null hypothesis? It doesn't say they accept the null hypothesis. Just because we don't have enough evidence to support guilt doesn't mean a person is innocent. So we just don't have enough evidence to say that they are guilty. So even if jurors leave unconvinced of guilt, that doesn't mean jurors believe the defendant is innocent. Let's talk about what could happen in a court system, and it's the same as what could happen in hypothesis testing. So you have the null hypothesis and the alternative hypothesis. When the null hypothesis is true, what we're going to do is we're either going to reject it or we do not reject it. So let's say the null hypothesis is true and we do not reject the null hypothesis. That is a good decision. If the alternative hypothesis is true and we reject the null hypothesis, that's also a good decision. Now there's two types of errors we can make. There's a type 1 error and a type 2 error. Let's talk about a type 1 error. So that's when the null hypothesis is true and we reject it. Let's think about it in a court system. A person is innocent, and we reject the fact that they're innocent. What does that mean? An innocent man is put behind bars. How is this error made? Well, the evidence supports the rejection of the null hypothesis. A type 2 error is when the alternative hypothesis is true, but we don't reject the null hypothesis. That means we don't have enough evidence to say that the alternative hypothesis is true. So in terms of court, is a person is guilty, but we don't reject the fact they're innocent. So that means a guilty man walks free. This error is made when we don't have enough evidence to reject the null hypothesis. Now, in terms of court and a person being guilty or not guilty, which type of error is worse? Is it worse to put an innocent man behind bars, or is it worse to have a guilty man walk free? I would say it's worse to put an innocent man behind bars. And that's the same assumption we're going to make with hypothesis testing. We're going to design a test so that we are conservative. We don't want to put an innocent man behind bars. So you're going to have to build a very strong case for us to reject the null hypothesis. So the hypothesis testing procedure is based on the initial assumption that the null hypothesis is true. What you're going to do is you're going to take a random sample from the population of interest, and you're going to collect data, and that data is going to provide evidence that supports or does not support the null hypothesis. Now we're going to reject the null hypothesis in favor of the alternative hypothesis only if the sample evidence strongly suggests the null hypothesis is false. If the sample does not strongly contradict the null hypothesis, we're going to continue to believe in the plausibility of the null hypothesis. Now, at the end of a hypothesis test, there's two possibilities, two outcomes. The first one is we reject the null hypothesis in favor of the alternative because there's sufficient evidence in the data. The second option is that we fail to reject the null hypothesis because there's insufficient evidence in the data. Now, the truth or falsity of a statistical hypothesis is never known with absolute certainty unless we can examine the entire population. In other words, we might make a mistake, but the way that we design a hypothesis test is we would rather make a type 2 mistake than a type 1 mistake. And our goal is to minimize the type 1 error. Now, I mentioned this concept of strong evidence. What is strong evidence? It depends on the problem, but in general, we don't want to reject the null hypothesis more than 5% of the time. This is called the significance level, and we denote it with an alpha, a Greek letter alpha. So we want alpha to be equal to 0.05 unless we're told otherwise. So somebody may say they want the significance level to be 1%, which would mean we don't want to reject the null hypothesis more than 1% of the time. So if the null hypothesis is true, the significance level alpha indicates how often the data lead us to incorrectly reject the null hypothesis. So here I have an image of a normal distribution. And notice that I have a confidence level of 95%. And when I have a confidence level of 95%, that means 5% of the data is in the tails. And because this distribution is symmetric, 5%, if we divide it in half, we get 2.5 in the left tail and 2.5 in the right tail. So how a hypothesis test works is you tell me the assumption that P is equal to, let's say, 0.2, like in the daily loneliness. I'm going to build a confidence interval around that 0.2, and I'm going to see if a sample statistic lives in that confidence interval. If it lives in that confidence interval, then that means we do not reject. If it lives in the tails outside of the confidence interval, then we reject. We'll do a problem where I explain this further, but the 5% refers to living in the tails, and the confidence level is living in the middle of the graph. So when you see 5% significance, If we're doing something called a two-tailed test, I'll explain that later, but that's the same thing as 95% confidence. So we talked about making a confidence interval. So 5% significance is 95% confidence. 99% confidence would be the same thing as 1% significance. If we add these two numbers together, we get 100% because the 1% is what's living in the tails and the 99% is what's in the middle of the graph. So if I said, I want a 2% significance level, that means 98% confidence. The state of Wisconsin would like to know if the percentage of its adult residents who consumed alcohol last year is different from the national rate of 70%. To help the state answer this question, they survey a random sample of 852 residents and found that 570 of those residents consumed alcohol last year. Test at the 5% level of significance whether the true percentage of Wisconsin adult residents who consumed alcohol last year is different from the national rate. Our first step is to figure out what is the null hypothesis and what is the alternative hypothesis. The alternative hypothesis is given to you in that last sentence. They want to know if the true percentage of Wisconsin adult residents who consumed alcohol last year, so that's P, is P different means not equals to the national rate. Well, the national rate is 70%. So notice here, the second thing in this last line is the alternative hypothesis. And the null hypothesis is that it's not different, that it's P is equal to 0.7. We're also told another piece of information. We're told that 570 of 852 residents consumed alcohol last year. So that is a sample, which is going to give us a statistic. So P hat is our statistic, just 570 over 852, and we get 0.67. Now our goal is to see if that 0.67 is too many standard deviations away from the mean, P is equal to 0.7. What is too many? Well, we're told in this problem we want to test at the 5% level of significance. 5% significance means 95% confidence. So what we're going to do is we're going to take P and we're going to build a 95% confidence interval around it. And the goal is, so when we build a confidence interval, we're going to get a lower bound and an upper bound. We want to see if that P hat lives inside those bounds. Now for 95% confidence, the z-scores that correspond to those bounds are negative 1.96 and 1.96. So we don't want to be more than 1.96 standard deviations away from the mean. So the first thing we need to do is figure out if our sample is large enough in order for us to make a confidence interval like this. So we're going to take n times p and n times 1 minus p and see if both of those numbers are greater than or equal to 10. Now n is the size of the sample, 852, and p is 0.7. Now be careful here. In the past, when we made confidence intervals, we used p hat, the 0.67, when we did n times p and n times 1 minus p. Because we know the true P, we're not going to use P hat. The assumption is that P is equal to 0.7. So that's what you're going to use. Whenever we do any formulas involving standard deviation, checking to see if a sample is large enough, we're not going to use P hat. In fact, we're just going to hold on to P hat until the very end. So all of the formulas you're going to see are going to involve the assumption P. So 852 times 0.7 is about 596. And 852 times 1 minus p is about 256. Both of those numbers are greater than 10, so we can continue. My next step is to find the standard deviation. Remember that a binomial distribution, when we have a sufficiently large sample, becomes a normal distribution, and the standard deviation is the square root of n times p times 1 minus p, all divided by n. So if you calculate that, you get 0.016. Double check that you can get the same number in your calculator. Now there's two different options for the hypothesis test. The first option is very similar to what we did with confidence intervals, and the second option involves z-scores. I'm going to go over the first option because it'll probably make the most sense at this stage. And then I'm going to redo this problem, but I'm going to go over it with z-scores, okay? So let's start with option 1. What I'm going to do is I'm going to create a 95% confidence interval around P. So I'm going to take P and I'm going to add and subtract 1.96 times the standard deviation. We just found the standard deviation. It was about 0.016. So if I take that 0.016 and multiply it by 1.96, I get 0.031. I'm going to take that 0.031 and add it and subtract it from 0.7. And if you do that, you'll get 0.669 and 0.731, which is the same thing as 66.9% and 73.1%. So what does this confidence interval mean? So this is saying, if the true rate of Wisconsin residents who consumed alcohol in the last year was 70%, then if I go out and get a sample, a random sample that is sufficiently large of Wisconsin residents, and I calculate the percentage of those residents who consumed alcohol in the last year, I'm going to get something between 95% of the time, I'm going to get something between 66.9 and 73.1. Now let's look at our statistic. We got 67% or 0.67. That number falls in that confidence interval. So that tells me that this is plausible. If the real rate was 70%, I should get something between 66.9 and 73.1, and I did. That 67 is close to that lower bound, but it's in between those two numbers. So I did get something in between those two numbers, which means I failed to reject. There's just not enough evidence to support the claim that the true proportion is different than 70%. So if the null hypothesis is true, then 95% of the time, the sample statistic should fall between the range of 66.9 and 73.1. Now, our p hat, 67%, is in this range of plausible proportion values. Therefore, the data does not provide sufficient evidence to reject the null hypothesis. It is plausible that the true percentage of Wisconsin adult residents that consumed alcohol last year is 70%. We didn't prove that it couldn't be 70%. Now let's see a second way of solving the same problem. Okay, we already know the answer to this. We're going to fail to reject. It is plausible that the true proportion of Wisconsin residents who drink is 0.7. Now, the second way we can do this is using z-scores. What we're going to do is we're going to see if we're in the tails of the normal distribution. So here in the bottom right-hand corner, you see the normal distribution. By checking to see if we're in the tails, if I'm in the tails, that means I'm not inside the confidence interval. If I'm not in the tails, that means I'm in the confidence interval. So if I find the z-score that corresponds to this p hat, what is the z-score that corresponds to 0.67? If it's bigger than 1.96, or if it's smaller than negative 1.96, that means I'm in the tails, which means I'm going to reject. But if the z-score is somewhere between negative 1.96 and 1.96, that means I'm not in the tails, I'm in the confidence interval, and I fail to reject. So how do I find the z-score that corresponds to my statistic? Remember that the z-score formula is x minus mu divided by sigma. Here, instead of mu, which is the parameter, I have p, which is the parameter. Instead of x, I have p hat. So it's almost the same formula. It's p hat minus the parameter p, and we divide by sigma. So if you take 0.67, subtract 0.7, and divide by 0.016, you get negative 1.911. You get negative 1.911. So this number is not less than negative 1.96, and it's not bigger than 1.96. It's not in the tails. So we're inside the confidence interval, which means we fail to reject. I want to mention, if we go back a few slides, we got this range. You see the 66.9 to the 73.1? That was the range. And we said that 67 was in that range. It was really close to the lower bound, though. And remember that lower bound. The lower bound corresponds to the z-value of negative 1.96. And because 0.67 is so close to that 66.9, its z-score should be close as well. So the z-score of 66.9 is negative 1.96. And we found that the z-score for 0.67 is negative 1.911. Notice how close they are. All right, I'm going to leave you on this problem. In the next video, we're going to cover this problem, but I want you to at least get it started and see if you can come up with all of the important formulas like the null hypothesis, the alternative hypothesis, what is the statistic, and write all that stuff down and see how far you can get. You can choose either option 1 or option 2, to try to solve this problem, and then we'll solve it together in the next video.